Okay, good morning, everyone. Well, good afternoon. Welcome to this month's Biophysics in Africa talk. Our speaker today is Dr. Oludari Ugonyemi from Nigeria in the Department of Biochemistry, College of Medicine, at the University of Ibadan in Nigeria. Dr. Ugonyemi is a 2023 PhD graduate of the University of Ado Ekiti. His research focused on bioprospection of novel neutrophils and drug candidates with specific emphasis on metabolic diseases, neurodegenerative diseases, and infectious diseases, and he has publications in cancer as well. He approaches this through enzyme inhibition assays and machine learning and computational biology, artificial intelligence. He's published extensively in peer-reviewed journals, has a H-index of 16, and is very active in the BioStruct Africa network. And without further ado, I'll turn it over to the speaker. Go ahead.
Yeah, thank you very much for the kind introduction. I want to appreciate the organizers for giving me the opportunity to present for this month's version about biophysics in Africa. And I'm an early career researcher and just trying to organize my group. And we started with a very cost-effective workflow, computational work, and we hope to build on from here. So my emphasis is many of the things I'm going to be presenting, they are preliminary, and we are moving on with the work. So I have the privilege to present on AI-driven structural insight into 11-beta hydrosteroid dehydrogenase type 1 inhibition. And then the second part is exploring steroidal pregnanes for metabolic disease therapy. As a background, over 537 million people of whom 75% of whom are from low and middle income countries are diagnosed with diabetes mellitus in 2021. And this is projected to increase enormously by 2045. And from IDF website, captured like a week ago, is still growing till 2050. So it's a problem that needs urgent attention. So as part of the background, what has been driving therapeutic target validation or identification and validation have been to overcome the limitation of current treatments. Many treatments currently used, they are problematic, the suboptimal potency, side effects, and so on. And many of them cannot address disease complexity like metabolic diseases, a very complex disease, and to enable more effective, selective, and personal therapy. So a few years ago, HSD, ongoing, I will be calling beta hydroxysteroid, HSD1. HSD1 was seen as a featured target. And of course, it's an active area where people are working currently. So what about the target? To put it in biological context, the biochemical role is to convert cortisone to cortisol. And this way we have another one, a distant homologue, HSD2, that converts cortisol back to cortisol. They work in opposite direction, but they are compartmentalized by tissues, by their organs. HSD1 is mostly present in the liver, in metabolizing organs like liver, like adipose tissues, the brain, while HSD2 is common in the kidney, in the placenta, and in the intestine. So they are compartmentalized. And to talk about, briefly, to talk about cortisol, it's a molecule that affect a lot of metabolic processes. I'm not going to go into details, but we can see that many organs are affected, many biochemical pathways are affected. I'm going to pick on liver and adipose tissue. It drives up gluconeogenesis, glycogen storage, lipogenesis, and liver, and in adipose tissue drives up lipolysis, fatty acids. So it's central to metabolic health. So in this case, in this way, cortisol can increase the blood glucose level, central obesity, muscle wasting, hypertension, and so on and so forth. So the target now, HSD1 target, it's a protein, a protein that it's inserted into endoplasmic reticulum membrane, and but the bulk of it is in the cytosol. And one thing I like to pick from this is that it has Rossmann fold, which helps to bind to nucleotides. And of course, this is a protein depending on NADP for its activity as a coenzyme. And this is the 3D structure and the active sites. I'm still going to touch the active sites. The NADP bound and the cortisol bound, and this is how it works. Then the active site architecture, where I really want to lay emphasis, it has subpockets, and we have specific amino acids that drive the activity of this enzyme, particularly serine 170 and tyrosine 183 that conducts hydrogen bond interactions with the substrate cortisol. And of course, some van der Waals interactions will also be present, particularly for ligands that will insert deeply into the pocket, will engage in more of van der Waals forces. So why target this? With few things I've said, I'm sure we've been wondering, we would have got reasons why these have to be targeted. It is tissue specific. As I mentioned, it's located in the liver, adipose tissue, and a few other organs. And the clinical relevance, it's as most focus has been on diabetes, but it is emerging evidence is showing that it's central to metabolic health, touching on hypertension, diabetes, obesity, and so on. So targeting it can help. Of course, reports have shown that targeting this enzyme can increase insulin sensitivity, increase glucose tolerance, reduce gluconeogenesis, reduce fasting glycemia, reduce glycated hemoglobin, and postprandial hyperglycemia. So generally, it has the potential to reduce metabolic burden in individuals. So I'm going to touch on structural scaffold of pregnane briefly, because it's in my title. And pregnanes, steroidal pregnanes, they have this core, cyclopentanoparhydrophenanthrene ring, which is also in cholesterol and in steroid hormones. So it is steroidal in nature. And this is looking actually bulky. I'm going to emphasize that bulky nature of this scaffold. So I'm going to briefly, before I move on, I will touch on the role of AI. So AI has made an inroad into almost all the life cycle of drug discovery. And in our own case, we're talking about its discovery, the number two, its discovery to discover it efficiently, and to different tools have been used in this phase of drug discovery. So I'm not going to go into details of other steps in drug discovery. So the research gap. So far, about as we're going to see, about 5,000 compounds that have been reported to have effect on the activity of this enzyme. Many of them fail at the clinical trial level. So we are curious that why are they failing? So we decided, so that there's limited structural insight into HSD inhibition. So more understanding of the inhibition mechanism can actually help to prioritize some hits over others. Then natural products from the work from our lab is coming in at this point because we've been working on steroidal pregnane for some time. These steroidal pregnanes, the glycosidic, the glycosides and the core structure masectoid was actually were isolated from a Nigerian medicinal plant. We call it locally Itazi, and the name is Gongronema latifolium. So it was extracted, and we got these 4 compounds. We've been testing these compounds over time, but one thing is that the activity, they all tend to help in several conditions. A colleague tested it on hypertensive rat. It showed positive results. From our lab, we tested it against sucrose-loaded rats, and it was able to help alleviate hyperglycemia. So we became curious that this steroidal pregnane with the kind of with the kind of structure it has and the multi-target potential, it may help in metabolic syndrome generally, rather than just diabetes. So the next thing that comes to mind is HSD1, which is central to metabolic diseases. So natural products, including steroidal pregnanes, are underexplored, and steroidal pregnane scaffolds, despite having biological relevance, as reported by several researchers, including work from our lab, they are under-optimized. So where the aim of this study is to provide structural insight into HSD1 inhibition, and at the same time identify candidate steroidal pregnane inhibitors using AI-driven molecular modeling approaches. So we hypothesized that steroidal pregnane could actually, natural steroidal pregnanes can actually occupy the cortisone binding pockets. While occupying this pocket, it can adopt orientations that differ from the known drugs and the native substrate, that is cortisone, because of its substitution at carbon 3 and at carbon 17, and of course other moieties that may be attached to the steroid core. So we adopted this workflow, and that's what I'm actually trying to showcase here today, that this workflow is what we have established in a lab, particularly in low resource settings, to refine its compounds before biological evaluation. So briefly, we checked on the biological bioactivity data on HSD1 on internet, on databases, including Chainbuild database. And we noticed that IC50 were highly reported. KI was also reported. AC50 and some other ones were reported. Ranking them, we picked on IC50 that has the most robust data set. So cleaning it up, we removed salt, we removed the incomplete scaffold and all that. Then we came up from 4,236 IC50 unique unique molecules. We came up with 3,158 unique molecules after cleaning. So after checking this data set, and we are sure of we are sure of the robustness, the quality of the data. So we subjected this to fingerprinting for machine learning training. We involved several machine learning models in this study, both supervised and unsupervised, depending on different objectives that we had in this study. So several ones were trained. I'm going to talk about them. And also pregnant structures. We curated pregnant substructures focusing on the core scaffold. So we hello, I hope you can hear me.
Yes, we can hear you.
Okay, great. Thank you. So after removing duplicates, then we also generated the fingerprints for pregnant. Then we subjected these pregnates to machine learning prediction, ranking it. We built a PIC50 machine learning model, QSAR model. We also built a machine learning for predicting KI. I de-emphasized the PKI prediction in this presentation to save time and space, but it's part of the workflow. So we came up with high priority hits from machine learning prediction. We subjected this to structure analysis through molecular docking, molecular modeling, MD simulation, and MMGBSA to refine our eight. We came up with 3 8s, and eventually these 3 8s will be ready for biological validation. So I'm going to go into the result. So this is the chemical space of PI for HSD1 inhibitors as retrieved from Chainbuild. Yes, Chainbuild. The data set was not very robust on binding DB, so we dropped binding DB since we got enough from Chainbuild. Of course, it's understandable. The more the data, the better. But we just have to restrict our analysis to Chainbuild inhibitor data set, and the data looks good. The data set looks good. So we wanted to know, we wanted to explore some of the properties that may contribute to activity. So we divided the data, we splitted the data into active and inactive based on the PIC50. So our threshold is PIC50 greater than or equal to 6.0. So any molecule that is higher than 6.0 is considered active, and less than that is considered inactive. So exploration, from exploration, molecular weights, the molecular weight of active is higher in distribution than that of the inactive, this suggesting that molecular weight may contribute, although molecular weight should be treated with caution too. And log P, which is an indication of the lipophilicity, and the active compounds tend to be more lipophilic than the inactive. We checked other ones, but these are the ones that stand out to contribute to the bioactivity, showing that active compounds are different in distribution than the inactive compounds. So balancing molecular weight and log P is very important in pharmacokinetics. So we have to present this on a scatter plot, log P versus molecular weight, so as to see the distribution of the data on the plots. And the active, of course, we have so many active, and the inactive compounds, they cluster around molecular weight of less than 500, between 300 and 500, and log P between 2 and 6. Of course, this is still in the range of Limpinski rule, that molecular weight should not be more than 500. 500, and log P should not be more than 5. So this is indicating that the chemical space is actually good. Then splitting the data, getting ready for machine learning training, we splitted it, and we had to plot the graph on figure 3A to see the distribution, and they are well distributed. The test data and the trained data, they have good overlap. Then TSNE plot also show good representation, good overlap, and good overlap. So as to repose, what confidence should we repose in our splitting? So with this, we are confident that we can go ahead with machine learning training. So the first unsupervised learning classification model we trained was Bernoulli naive Bayes classification model. And this is to help us to explore the fragments, the debates, the fragments that may contribute to activity, and identify those ones that may that may reduce activity, HSD1 inhibitory activity. This model achieved accuracy of 83% and precision of 95%, showing that it's a good model. We're confident about it. And ROC, area under curve, having 83%, and we can trust, to some extent, we can trust our model. Although the model is with the confusion matrix, the model has a moderate moderate misassignment of activity. Is assigning while 92 compounds were active, the model is showing that they are inactive based on this confusion matrix. And well, it is still it's still considerable. So we went ahead to perform the feature importance and to get the fragments that are really responsible for the inhibitory activity of this compound across compounds. So we were able to get so many bits, so many fragments, and the top 20 are illustrated in this figure. And we just picked randomly, we picked the top fragments. These are compounds, and the fragments are highlighted. If you can see my cursor, they are highlighted in these compounds, and these are sorry. So these were observed to be associated or linked with high activity. As you can see, the PIC50 value of these compounds. And what's the implication of this? In drug development, attention should be placed on this kind of scaffold. Of course, it's a rigid, we can notice that the scaffold is rigid in nature. The rigidity is more emphasized in fragment 260, where we can see that this, sorry. If you can see my cursor, this scaffold is common to all the compounds and it's rigid too. Unlike the fragments that I call them liability fragments because they reduce, based on our study, they reduce the activity of the compound. So in drug development, in lead optimization, these fragments should be de-emphasized, while those fragments that are contributing to the activity should be emphasized in drug optimization. So those are the insights we could get representing this on PCA. We were able to cluster this inhibitor data set into four clusters, and we're able to identify the most active and the least active in each cluster. This could also help in identify activity promoting scaffold and activity reducing scaffold. So this is a bridge between our inhibitor data and our pregnant data because we needed to check what variance will our pregnant data have with the reported experimental inhibitor data set. Yes, they are very close. Looking at the variance, the component 1.6%, component 2, 1.1%, they are very close. The variance is very low. But the insight we can get from this is that steroidal pregnant, which is in yellow, steroidal pregnant is occupying a novel chemical space that has not been explored. So as to have confidence in moving forward with our steroidal library. So with this, we went forward to train machine learning QSR model for predictive models. And we assessed 42 we ran them based on R-square value and the root mean square value, and random forest regressor came top with the highest R-square value of 0.65 and the lowest RMSC of 0.7 among all the machine learning models. So we went ahead to subject this RFR, random forest regressor, to cross validation. We used 10-fold cross validation, and it achieved an average value of 0.64, which is moderate enough for confidence in our model. So for that to validate, we presented the data, the predicted data and the experimental data on a scatter plot, and as we can see, is showing strong correlation. And this is also giving this gives us a level of confidence in our model. So going ahead, we predicted the PIC50 value of the pregnant data sets, and figure 11.11b, it shows the distribution of the predicted pregnant compounds, and many of them are actually active and just few of them are inactive based on our threshold. To remind you, our threshold is 6.0 PIC50. So many of them are actually active, while some of them are inactive. So it's time to do the structural and interaction analysis. to as a way of validating the machine learning prediction. We started with molecular docking, and our pregnant compounds are in blue color, blue bars in figure 12A. The substrate, cortisone, if you still remember cortisone, the substrate of HSD1, and the reference drugs, especially the co-crystallized compound R1, that is carbenolozone. R1 is the co-crystallized compound with the protein we used for the docking. And we can see that three compounds stood out. P1 to P3 stood out higher than in binding score, in docking score, lower than all the reference compounds, and even the substrate, the substrate of the enzyme. And their structures are presented in figure 12B alongside with their PIC50 values, the PKI values, and the docking score. So we're moving forward with three compounds from this point. The names are presented on the slide. P1, P2, P3 are considered as our EAT compounds, and corticosterone, the substrate, and the reference drugs the names are presented. So docking, we had a very good insight from this. If you can see the surface view in the binding pocket, we can see that our pregnanes add better insertion into the binding pockets, while the reference compound add some level of insertion, but also in addition, also use some surface surface interactions. But it's important to note that our compounds actually had deeper insertions, and they interacted with the key amino acids like tyrosine 183 I mentioned earlier, and several of them by hydrogen bonds and hydrophobic interactions, many of them. These are very critical amino acids on the active sites of the enzyme. So what we learn from this is that our compounds may bind better. I'm carefully choosing my words because this has not been, I've not been subjected to experimental validation. So we, as a way of further validation, we subjected this to 100 NS, 100 NS molecular dynamic simulation, and we computed the dynamic properties like root mean scale deviation, radius of gyration, hydrogen bonds content, and surface accessible surface area SASA. So from the results from RMSD of the complexes, we can see that stability was achieved around 20 NS, and till the end of the simulation, we had stability, and some of the pregnanes were actually more stable than the reference drug. Of note is compound 1P1 with lower RMSD. But the important thing is that all the complexes actually achieved stability, because the fluctuations are within 2 angstrom. So that indicates stability. Then radius of gyration is it indicates the compactness of the complexes. And of course, as we can see, it's less than 2. The fluctuations are less than 2 angstrom, showing that they have well compact. They have well compact structure. The hydrogen bonds, of course, that can the hydrogen bond is the strongest non-covalent bond, And the more hydrogen bonds you have, the stronger the interactions. And we can see where we have in the whole biomolecular system, we have so many hydrogen bonds, up to 1,370, 13,750 hydrogen bonds for all the complexes. So they are rich in hydrogen bonds. And of course, the accessible surface area also shows stability. So for root mean square fluctuations, that shows two things: the stability and the residue level fluctuations. We can see that the fluctuations around the active sites containing serine 170 and the key amino acids achieved high flexibility, high fluctuations up to about 4.5 angstrom. And this shows that binding may be complementary. I mean, the protein was flexible at this point to accommodate the ligands of all of them. But P2 seems to stand out at this point. P3 interactions with P3 led to fluctuations of the protein unusually around between amino acid 160 and 170. This may indicate this may have a very critical implication, and insight can be drawn from this, maybe going forward in subsequent analysis. So RMSF is showing stability, and at the same time is showing the flexibility required for interaction with the ligand. So we took the trajectory of the trajectories of the MDS, and we subjected it to clustering to assess the behavior of this complex in the course of the simulation. And in the course of the simulation, we clustered them into three. It was automatically clustered by TT-clust, a tool, and we picked representative structures from each cluster. So for cluster one, we can see this is pregnant 1, and for cluster 1, we can see it's rich in hydrogen bond linked to some critical amino acid in the active site. C2 has no hydrogen bond, but hydrophobic interaction. And cluster 3, this is still indicating some level of stability in the course of the simulation. And for P2, we did the same. P2 seems to have more interactions in the course of the simulation, enriched with hydrogen bonds and hydrophobic interaction. More importantly, we have more hydrophobic interaction, that is van der Waals bonding. Then for P3, the compound 3, we observe similar trend. So to validate the docking score, we subjected this to the complexes to MMGBSA binding energy assessments, and analyzing this based on different contributions. We can see that for P3, P1 and the reference drug, the van der Waals forces, free energy of binding contributes significantly to the binding. And we can see some other one like GSOL, GGAS, EGB. This represents the binding, the binding contribution from different factors that determines the strength of the binding affinity. So this is still validating the docking score, and the eye binding interaction with HSD1. So key takeaways from this study, we were able to identify 3 compounds from a library of steroidal pregnanes as its compounds. And comparing this back with the reference compound, we can see that they tend to have higher scores in terms of PIC50, PKI, and free energy of binding. And they are suggested as promising compounds subject to experimental validation. So in this workflow, we've been able to demonstrate that AI reduces screening complexity. We're able to deal with a lot of data and simplifying the screening and achieving more with AI. And MDS, which is a computational validation tool, helps to refine docking predictions as I presented. Then overall, steroidal pregnanes show strong inhibitory potential. Limitations of the study, it is in silico bias because all the insights are based on in silico, and the data set size is actually moderate for IC50, but for KI, very low. That's why we did not really lay emphasis on PKI, and we laid the most emphasis on IC50. So there's need for experimental validation. So future work in a lab, and at this point, we are open for collaborations. With in vitro enzyme assays, yeah, we do that in a lab. A cell-based validation, we need collaboration to take this in silico hits forward. If this is validated experimentally, then this can lead to lead optimization, and of course, eventually we can be able to validate this experimentally with do structural elucidation of the interaction using X-ray crystallography or cryo-EM. So especially at the point of experimental validation of the structure in complex with this pregnant, we really need a collaboration, and we need help. So AI-driven structural biology overall can unlock the therapeutic potential of underexplored natural scaffolds. I'd like to acknowledge people that have contributed immensely to this study, and they are part of the lab, they're part of the team. I appreciate them. Abdullah Nafisat, she just finished her MS, so she's a PhD candidate currently. Adeshewa, by the right, the second lady, the first lady is Nafisat, the second lady is Adeshewa. She's also done with a master's, and she's a PhD candidate. Olabuntu Babatunde also is currently a master's candidate, while the guy in suits is the guy in jacket is a PhD candidate in a university in the US currently. At this point, I'd like to appreciate Biostruct Africa. I'm part of this network all over Africa, trying to teach structural biology all over Africa. And I'd like to thank the leadership of Dr. Emmanuel Inji, who provided the funding for my training at some point, and that led to joining the network. The team has been doing great. The team has been doing fine all over Africa. And despite that, we are in a low resource setting in Africa, and structural biology tools are they are limited. We have limited access, yet we are motivated, especially those of us who really want to gain the skill. I'd like to thank everybody, all the participants, all the listeners. I'd like to thank you for your time, for listening to the workflow we've adopted. So I want to say thank you to Biophysics Africa for this kind of unique opportunity to present our work. Thank you.
Thank you. This is a very interesting talk.
Thank you.
Are there any questions for the speaker? I have a question as to whether or not computationally you can create a mixture of the ligands and see if there are kinetic factors. So you've done calculations, so there's like thermodynamically you can see what binds the most, but see if there's some kinetic factors by creating a mixture. Maybe you have to use like steered molecular dynamics to see if there's because of the flexibility or something like that, or the sequence of hydrogen bonding, there's a kinetic factor. Does that seem like a thing that maybe even AI can predict, or that you can show by simulations?
Yeah, if I got your question, if there's a connecting factor between, please, can you come again? I seem not to get the question.
So what I'm suggesting is you have a mixture of compounds that thermodynamically speaking will bind to the active site.
Yes.
But I'm wondering if there are kinetic factors in terms of the ability for the ligand to actually to this inhibitor to actually get into the active site.
To get to the active site.
And I'm wondering, like, are there differences in the thermodynamics of one inhibitor in the presence of another inhibitor? So will the inhibitors be competitive amongst each other, is what I'm trying to get to.
Yeah, it's not that we didn't go to that length, but it's noted. Thank you.
Is that Jabel Haji? You had your hand up.
Yes.
Please go ahead.
Yes. Okay. Thank you very much, Pase, for this fascinating and interesting work, which is very recent issue, especially for African, which is cost minimizing such computational aspects. Currently, I'm a PhD student. I'm finalizing my work. I'm from Ethiopia, Adama Science and Technology. Okay, Doctor, thank you for your presentation. What I want to ask you that just since I have some just concepts, currently we have just done plant disease identification using the spectroscopic technique and this machine learning. I need to ask you some concepts. This is data type, maybe three sources, text, sound, and image. In your study, what kinds of data source did you use? This is my first question. Other one is you may use raw data, pre-processing, feature extraction, and the data splitting. Data splitting is not clearly mentioned. While we split the data, it should be classified into three parts: training, validation, and testing. During your presentation, you mentioned the training and the testing only. I need to just gain some share experience from you regarding on your presentation. Thank you very much.
Thank you very much. Concerning the data source used, we relied heavily on chain-built database. And as we know, chain-built database contain several natural products or semi-synthetic products. And we actually biased the work towards natural products. So at some point, some semi-synthetic that have incomplete fragment, we remove them so as to have more of natural products.
Okay, doctor. Other one, for example, when we use the text data, ANN is applicable if we use a image, CNN, and some other. It depends on source of data. You use the one model, isn't it?
Hello, can you hear me, please?
Yes.
Yeah, thank you. So I attempted to answer the first question. I don't know that is satisfactory, but for the training and the test and validation set, yeah, for this study, I understand that we should split into the three, and but we were just comfortable with the training and the test. The training 80%, the test 20%, and we just went ahead straight to deploy it to predict the bioactivity of pregnanes. Of course, this is noted. We currently, the current work we do, we are using that method, test, training, and validation steps. Thank you.
Can I
Hello?
ask another question if there's no others? Are you in your department, in your lab, are you trying to make the protein in sufficient quantities for structural work? Have you done the expression? And are you ready to make crystals, or have you made crystals?
Yeah. Thank you. That's a thought-provoking question. For now, we do not have the capacity to do that. We hope to do that as part of the future work. We hope very soon we should be able to set up protein extraction equipment and possibly to start crystallizing. And I'm sure my mentor, I don't know if my mentor, Dr. Inji, is if he's online. These are some of the discussions we have been engaging in, how we can make that possible. So I hope very soon, and that's why we're also open to collaborations currently, but that's where we are going eventually. So in our lab, we've actually done a lot of in silico. So the next step is to start extracting the proteins and crystallizing the protein for structural elucidation. Thank you.
Are there any other questions for the speaker? So let me ask another just quick. So this, the enzyme that you're working on and the inhibitors, that would be for type 2 diabetes. Is there, what does the literature suggest in terms of the role it could play for type 1 or type 3 diabetes? I mean, so what they do, what this enzyme does is what it prevents cortisols from converting, right?
Most work they're on type 1. They're on type 1 because many of the models were strep model, which is mainly type 1. And currently we are trying to extend that to type 2. But the main focus of the emphasis here now is these targets can be used for metabolic syndrome generally, because most of the inhibitors of this protein that have been identified, over 170 of them that entered clinical trial, Many of them did not make it, and they have suboptimal potency compared to metformin. So
Yeah.
boxing it into type 2 like metformin may take a while, but there's promise in general metabolic syndrome.
Understood.
Thank you.
Well, if there's no further questions for the speaker, let's give him a round of applause.
Thank you.
Let's see. How do you do that? Right here. And then I put into the chat
Thank you.
the there's a published article based on today's presentation. It's the name of the journal is Computational Biology, I think.
Yeah.
And-
Computational biology and chemistry.
Yeah,
The journal
Computational
where it
Biology
was
and Chemistry.
published.
And it's already online, even though it's supposed to be an August 26th edition, but it's early online. And then I invite you actually to look up this speaker on Google Scholar to see his bibliography of published works, because they're all very quite interesting.
Thank you.
I mean, he's well on his way of being a leader in connecting structural biology and human disease states. So that's across metabolic diseases, cancer. I think I saw one on acetylcholinesterase. So
Yes,
neurological
cholinesterase.
diseases. So please, yeah, look up the speaker, and I hope we can have you back again soon to talk about some of your other work.
Yeah, I'll be glad.
Okay. All right. Thank you, everyone. If there's no further questions, we'll close the session.
Thank you, everyone.
Thanks. Let's stop the recording.